Well, thank you. Throughout most of my adult life, I've been engaged with the thought of Kurt Gödel, and I think I'd be an entirely different person if it wasn't for the rich set of insightful ideas that he left us. And I'm sure that most people in this room feel the same way, so you can understand that it's a great honor to receive this award. I'm grateful for the encouragement and support given to the area and the opportunity to continue to engage with the thoughts of that great mind. What I want to do today is talk about two themes from Gödel that are dear to me. The first concerns the nature of reason in mathematics, and I'm going to approach this through the question of absolute undecidability. That's whether there could be questions which are not just relatively undecidable to a given system, but in some sense absolutely undecidable. The second concerns the question of realism in mathematics, and I want to approach that through the question of whether there could be, in some sense, a bifurcation in set theory, in particular concerning the higher infinite. So what I want to do in this talk is give a very broad brushstroke overview of the development of the field, and with the hope of situating and motivating my current project. So I want you to just sort of get the big picture and not focus on particular details. So the story begins with the incompleteness theorems, the second incompleteness theorem. Assume that piano arithmetic is inconsistent, where PA is a shorthand for piano arithmetic, then piano arithmetic cannot prove a particular pi01 sentence, namely the pi01 sentence expressing the consistency of piano arithmetic. This raises two questions. Are such statements absolutely undecidable? And the scare quotes around that term are necessary. And do such statements signal a bifurcation in our conception of the structure of the natural numbers? And the answer, of course, is no. And Gödel was quick to point this out. He said in an unpublished manuscript of 1931, the year in which the incompleteness theorem was published, this statement is not at all absolutely undecidable. Rather, one can always pass to higher systems in which the sentence in question is decidable. In particular, for example, it turns out that analysis is a system higher in this sense than number theory, and the axiom system of set theory is higher still than analysis. So we begin with the natural numbers, which I'm going to draw in the form of a triangle, indicating that I'm really thinking of the hereditarily finite sets. And instead of piano arithmetic, I'm really thinking of the theory ZF minus infinity, which is bi-interpretable with piano arithmetic. And then Gödel's theorem tells us there's a sentence which can't be proved, namely con PA. But we follow the outline of Gödel's remark, and we iterate the power set and write down the associated axioms, namely the axioms of analysis or second-order piano arithmetic, and we find that we can prove that consistency sentence. But then another consistency sentence appears, namely the one for second-order piano arithmetic, but we just continue, go to third-order piano arithmetic. And we continue until we get to a level that satisfies ZFC. Its consistency arises. We go to the next level, second-order ZFC, catch the consistency sentence, and this situation continues. Now, depending on whether you're an optimist or a pessimist, you're going to have a different take on this. If you're a pessimist, you're going to think that for every level, there's a problem, namely the undecided consistency sentence. If you're an optimist, you're going to think for every problem that arises, there's another level that solves it. The trouble is that when one iterates the power set operation in this fashion, the greater expressive resources that become available give rise to much more serious candidates for absolutely undecidable sentences. So it was mentioned in the last talk that a dream is to construct natural mathematical sentences of first-order arithmetic that are independent and lie at various points in the interpretability hierarchy, perhaps bifurcating into incomparable elements. In the case of set theory, it turns out that that's pretty much the norm. Two classic examples of this are the statement that all Lebesgue measurable sets are projective and the continuum hypothesis. I'm not going to go into the details of those statements, apart from saying that they occurred in natural mathematical practice, and that the first statement concerns second-order arithmetic, or the second infinite level of the universe, while the second concerns the third. Now, these sentences were shown to be independent from ZFC plus, various small, large cardinals. If CFC is consistent, then ZFC plus CH is consistent, and hence you can't refute CH. This was shown by Gödel, and Cohen proved the companion result. Similar results hold for projective measure and a broad array of mathematical statements, and set theorists using these techniques and elaborations of them showed that many other statements are independent, so much so that what may have started off as a dream started turning into something of a nightmare. So here's what Gödel did. He started with V, and he carved out an inner model by iterating the definable power set instead of the full power set, and the resulting model satisfies CH. Cohen did something much more subtle. He created what one might think of as an outer model, an extension of the universe by a method known as forcing, and in this talk I'm going to concentrate on set forcing, in which the continuum hypothesis fails. So our questions resurface at this point. Are such statements absolutely undecidable? Do such statements signal a bifurcation in our conception of the universe of sets? The situation is now much more delicate. It won't do to just iterate the power set one more time to capture these sentences. But perhaps if one iterates the power set far enough, then one will. Perhaps if there are very large levels of the universe of sets, then these sentences will become decidable. The statements that assert that there are very large levels of the universe of sets are known as large cardinal axioms or axioms of infinity, and that's going to be the focus of my talk. There are two questions that immediately arise concerning them. First, are they justified? And second, do they do the trick in reducing incompleteness? So I'll talk first about the question of justification. Gödel drew a fundamental distinction between intrinsic and extrinsic justifications of new axioms. When discussing intrinsic justifications, he mentions the existence of inaccessibles, molocardinals, and these are small, large cardinal axioms in a very rich hierarchy. Gödel says that these axioms show clearly not only that the axiom system of set theory as used today is incomplete, but also that it could be supplemented without arbitrariness by new axioms, which only, and this is the phrase I want to stress, unfold the content of the concept of set as explained above, where above he explains the iterative conception that I drew a picture of earlier. And he talks of these axioms having intrinsic necessity relative to the iterative conception of set. On the other side, we have extrinsic justifications. Concerning this, he says, even disregarding the intrinsic necessity of some new axiom, and even in case it has no intrinsic necessity at all, a probable decision about its truth is possible also in another way, namely by inductively studying its success. And in a famous passage, he says, there might exist axioms so abundant in their verifiable consequences, shedding so much light upon a whole field, and yielding such powerful methods for solving problems, that no matter whether they are intrinsically necessary, they would have to be accepted at least in the same sense as any well-established physical theory. So I want to first talk about intrinsic justifications and then turn to extrinsic justifications. So intrinsic justifications are supposed to unfold the content of the concept of set. Now, an idea inherent in the iterative conception of set is that the universe is absolutely infinite and hence cannot be described from below. So the idea is you take a purported description of the universe of sets, and since it's absolutely infinite, what you've described is an initial segment of it. You've described a set. And reflection principles aim to articulate this. So schematically, a reflection principle has the following form. If V satisfies that some property holds of a given object, then there exists an earlier level of the universe that satisfies that the reflected version of that property holds of the reflected version of that object. And here I've left the nature of reflection unspecified, but it'll get specified progressively as we continue. So there's two issues. Are reflection principles intrinsically justified on the basis of the iterative conception of set? And do intrinsic justifications, do reflection principles lead to a significant reduction in incompleteness? Now, concerning the first, I think that there are philosophical problems with justifying certain reflection principles. But I don't want to go into that because I think that the mathematical situation is much clearer. And one can show that even if one can give a philosophical justification of reflection principles of higher order, let's say, then it won't be of much help because they're either weak or inconsistent and hence don't lead to a significant reduction in incompleteness. So here's the situation. If you take ZFC and pull away infinity and replacement, and then you add in first-order reflection, where you consider first-order formulas, a parameter is a set and it reflects to itself, then you can reprove infinity and replacement, which are the main axioms of extent in ZFC. And then if you go to second-order formula, higher-order formulas with second-order parameters, then you get inaccessibles, malos, weakly compacts, and indescribables. And to reflect a second-order parameter, the second-order parameter will be a class like A in V. To reflect down to V alpha, you just ask, what would things look like if you were living in V alpha? Well, you would reflect down to A intersect V alpha. So these principles give certain large cardinals. They justify certain large cardinals, assuming that they themselves are justified. They give inaccessibles, malos, weakly compacts, indescribables. The trouble is that as soon as you go to third-order parameters, you get the strongest large cardinal of all, 0 equals 1. So one has to pull back. Now the counterexample that arises motivates a certain restriction on the formulas that's necessary. You have to restrict to what are called positive formulas, and I'm not going to discuss that for reasons of time. But Tate initially isolated this necessary restriction and initiated the study of general reflection principles, and it leads to a hierarchy. The general form is gamma mn, but I'm going to concentrate mainly on the first level, where we have 2 in the superscript, and distinguish between that and all of the remaining levels. So the first theorem is that if there's an Erdős cardinal, kappa omega, then there's a level of the universe which satisfies gamma 2 n reflection for all n. So all the reflection principles on that first layer that I indicated are consistent relative to this large cardinal axiom. Now this large cardinal axiom is quite weak. It's consistent with V equals L, and so it follows immediately that these reflection principles cannot settle our two questions, projective measure or the continuum hypothesis. But Tate showed that those reflection principles are much stronger than what one gets with just second-order parameters. They imply the existence of ineffables. So there's hope that if you go on further to the third layer or the fourth layer, you're going to get significant strength. But it turns out that right at the first layer, you get inconsistency. So this shows that right at the next layer. So this shows the first layer is weak, the second layer is inconsistent. One might think, well, maybe there's some stuff in between. And there's a way of making that precise. And the last theorem, which is stated informally, says that under a very fine calibration, any attempt to skirt inconsistency leads to weak principles. So we can say this: general reflection principles are either weak or inconsistent. They do not provide large cardinal axioms that yield a significant reduction in incompleteness. So the two questions, the two themes I'm dealing with are to be asked. Are projective measure and CH absolutely undecidable? Do they signal a bifurcation in set theory? Now, there could be intrinsic justifications of things other than reflection principles of an entirely different nature that yield a significant reduction in incompleteness. But I don't know of any, so I'm instead going to turn at this point to extrinsic justifications. And fortunately, they have great reach. So much so that Gödel thought that on the basis of extrinsic justifications and his faith in the power of reason, which is not unreasonable if you're Gödel, that large cardinal axioms would actually yield a generalized completeness theorem. And here's what he says. It's not impossible that for such a concept of demonstrability, namely provability from ZFC and true large cardinal axioms, some completeness theorem would hold, which would say that every proposition expressible in set theory is decidable from the present axioms plus some true assertion about the largeness of the universe of sets. And CH was proposed as a test case. Well, that would be fantastic. And I claim that a network of theorems in modern set theory make for a striking extrinsic case for many new axioms that settle many of the classical questions. I'm only going to be able to touch on a very small fragment of that case. So the first theorem that's of relevance is a landmark result of Martin and Steele. Assume that there are infinitely many wooden cardinals, and these are large cardinals far beyond the ones I've discussed so far. Then, projective measure holds. And in fact, there's a statement PD that holds. And that has a concrete consequence. It says that you can't take, well, there's a theorem of Banach and Tarski which says you can take the unit sphere, break it into finitely many pieces, move them around in rigid rotations, and put them back together to get a sphere of twice the size. You ask, can you do it with closed sets? No. Can you do it with Borel sets? No. Can you do it with projective sets? ZFC throws up its hands. The large cardinals come in and say no. Moreover, the above large cardinal axioms, and in fact that axiom projective determinacy, appear to be effectively complete, and here the scare quotes again are necessary, at the level of second-order arithmetic. And we can quantify this. What I mean to say is that when you consider a statement of second-order arithmetic, it appears that you're going to get the answer yes or no modulo those large cardinal assumptions. It's hard to find examples that are independent. And the reason is that our main method for establishing independence like that is set forcing. So Wooden showed that if there's a proper class of wooden cardinals, then statements about second-order arithmetic can't be altered by forcing. So you can't use that method to establish the independence of a statement about second-order arithmetic from the assumption that there's a proper class of wooden cardinals. And it's not that the large cardinals are throwing a wrench into the machinery of forcing. In fact, they're giving you more generics. Now, there's something I want to mention which is pretty much as an aside, but it's just for purposes of comprehensiveness. The case for that axiom PD is even stronger. In fact, there's evidence for the claim that all sufficiently strong natural theories imply PD. So if you move up the interpretability hierarchy and you land at natural theories, the claim is that they're going to imply PD. And here's just two examples. I won't go into the details. The first concerns concerns omega 1, and the second concerns forcing axioms. So you've got a structure on omega 1, the first infinite cardinal after omega, and then you've got this forcing axiom. They both imply PD. They both imply ADL of R. Those two theories have nothing to do with one another. They're from completely different realms of mathematics. In fact, they're incompatible. So you have incompatible theories that are all pointing to this one axiom. So we have extrinsic justifications of axioms yielding projective measure. Unfortunately, the above considerations do not lift to the level of the continuum hypothesis. In particular, by a result of Levy and Solovay, standard large cardinal axioms don't settle CH. But as an aside, an intriguing possibility is that there are new large cardinal axioms yet to be discovered which don't fall prey to the Levy-Solovay result and do settle CH. So the situation is this: the large cardinal axioms are settling the theory, effectively settling the theory of second-order arithmetic. But when you go to the next level, third-order arithmetic, right at the beginning, they don't work. So in choosing CH as a test case for his program, Gödel appears to have put his finger precisely on the point where it breaks down. And then back to the two themes, our question remains, is CH absolutely undecidable? Does it signal a bifurcation? So I think we're at crossroads. What we need to do at this stage is stand back and ask, first, what would it take to have an acceptable resolution of CH and the other questions of set theory? So that's on the positive side. On the negative side, what would it take to have confidence that such questions are absolutely undecidable or signal a bifurcation in set theory? So I think we need to examine the space of possibilities both for an acceptable resolution of CH and for the claim that there is no acceptable resolution. And that's what I want to start doing in the last part of the talk. So we saw that large cardinal axioms give a complete picture of second-order arithmetic, and complete in scare quotes, and in fact L of R, and I want to start sharpening that, start peeling away those scare quotes. Well, I'm not peeling it away with this picture, but so in this picture what I've done is I've shown that the level of second-order arithmetic, V omega plus 1, that's the power set of V omega, the hereditarily finite sets, is frozen. So we understand that in the sense I'm going to make precise. So what we're going to do is reformulate generic absoluteness, that is the unchangeability of second-order arithmetic via set forcing, by using a strong logic that's designed to mod out the effects of forcing. So here's the idea. You take V and you look at its forcing extensions, continuing off, and in fact we're going to look at rank initial segments of those, and you construct a logic which takes those as your test models. Just as first-order logic takes as its test models any models, so this strong logic is going to take as its test structures rank initial segments of generic extensions. And here's the definition due to Wooden. Suppose T is a countable theory in the language of set theory and phi is a sentence. Then T omega implies phi if and only if, for any rank initial segment of a generic extension, that is any model in this class of test structures, if it satisfies T, then it satisfies phi. So it's just the standard definition of logical implication, except where you restrict the test structures. Now, this logic is robust in the following sense. If you have large cardinals, then set force as you might, you're not going to change the consequence relation. So if one universe thinks that T omega implies phi, and you force and go to another universe, in that universe the people are going to agree that T omega implies phi. There's going to be no disagreements. So that's in contrast to something like full second-order logic. And there's a corresponding proof relation, denoted single turnstile phi, which I won't define. The definition's complicated, and it would take us too far afield. And it's also robust in the above sentence. And the analog of the soundness theorem is known to hold. So if T omega proves phi, then T omega omega implies phi. And so the natural question that arises is, what about the completeness theorem? And that's open. The omega conjecture says that if there's a proper class of Woodens, then for each sentence phi is going to be valid in omega logic if and only if phi is provable in omega logic. And I want to stress that this provability relation is not syntactic in the sense that it's sigma 0, 1. It couldn't be. It's not definable in first-order arithmetic. It's definable in third-order arithmetic. So it's syntactic only in the scare quote sense of the term. So now that we have this strong logic at hand, we can say that a theory T is omega complete for a collection of sentences gamma if and only if T omega implies phi or T omega implies not phi. And in this language, with this logic, we can reformulate that result of Wooden on generic absoluteness as follows. Assume Z of C and that there's a proper class of Wooden cardinals, then in this strong logic, Z of C is complete, that is omega complete, for second-order arithmetic. So you take any sentence of second-order arithmetic in the strong logic, you can prove it from ZFC or you can refute it. So that's a partial articulation of Gödel's expressed hope for a generalized completeness theorem. Large cardinals are involved, only we're bumping up the power of the logic. And we're just getting it for second-order arithmetic, not the entire hierarchy. Now, can you get it for the entire hierarchy? Well, no. By that limitative result of Levy and Solovay, standard large cardinals are not going to give you that ZFC is omega complete for third-order arithmetic because of the continuum hypothesis. But can one, through other means, have higher forms of omega completeness? Well, it turns out that if you add the continuum hypothesis into the picture, then you can. So Wooden showed in 1985 that under stronger large cardinal assumptions, ZFC plus CH is omega complete for the first layer of third-order arithmetic. That's sigma 2, 1. And that's where CH lives. Now you might think, well, that's a great thing about CH, but maybe there's a different axiom which also shares that feature, that it gives you a complete omega picture of sigma 2, 1. And it's fairly easy to show that up to omega completeness equivalence, CH is the unique such sentence. So if you have any other sentence, then it's omega complete for sigma 2, 1. So that might incline you to CH. But there's a companion result for not CH. Assuming the omega conjecture, which is the completeness theorem for omega logic, if there's a proper class of Wooden cardinals, then there's an axiom A such that ZFC plus A is omega satisfiable, and it's omega complete for the structure of H omega 2, which is a different way of stratifying the universe than the one I mentioned. But CH lives at that level. And any such axiom A has the feature that it omega implies that CH fails in that structure. Now, the question I want to ask is whether one can go further. And so this section is called an optimistic scenario and the prospect of bifurcation. So what I'm going to do is I'm going to start off by looking at a very optimistic scenario for getting a complete picture of the universe of sets, for realizing Gödel's hope or a modification of it. And then actually it's going to sort of slide into a scenario for bifurcation. So Wooden showed that if the omega conjecture is true, then there's no recursive set of axioms which will do this for sigma 2, 3. So if the omega conjecture holds, you might be able to get it for sigma 2, 2, that's open, but no recursive theory is going to do it for sigma 2, 3. And so this approach is going to fail at third-order arithmetic. But if the omega conjecture fails, then perhaps we can achieve more. Here's an optimistic scenario. So this is our situation. We've got an omega complete picture of second-order arithmetic, and if we add CH, we get an omega complete picture of the first layer of third-order arithmetic. Perhaps there's sentences, A naught through AN and so on, that give us an omega complete picture of the successive layers of third-order arithmetic until we fully have full of third-order arithmetic. And then being more ambitious, perhaps there's sentences A1, etc., that give us an omega complete picture of fourth-order arithmetic, and then fifth, and then sixth. And you keep going. Perhaps if you pick any specifiable level of the universe, V lambda, there are axioms, recursively enumerable, I'll call it A vector, which give you, modulo large cardinals, an omega complete picture of the theory of V lambda. So here's the scenario. For each specifiable fragment, V lambda of the universe of sets, there's a recursive set of axioms, A vector, such that ZFC plus large cardinal axioms, where I'm using that as a placeholder for anything, so I want the scenario to be as general as possible, plus A vector is omega complete for the theory V lambda. And the optimistic scenario adds the following uniqueness condition. If B vector is any sequence with this feature, then just as in the case of CH, you've got uniqueness modulo omega logic. So if this scenario were to be the case, then you would have a single omega complete picture of V lambda. So it would be a modification of Gödel's conjectured completeness theorem. You would say there is a sequence which gives it, and all such sequence give it. But the problem is maybe there's the sequence A vector, and then there's the sequence B vector, which is also omega complete, and you can't choose between them. So Wood and I recently proved that uniqueness must fail. And here's the theorem. If there's a proper class of Woodens, and you take v lambda to be some specifiable fragment of the universe, and you suppose that you've got an A vector which will give you an omega complete picture for that, the theory of v lambda, then there exists a B vector such that it also gives you an omega complete picture, but the two theories differ in omega logic on CH. So in one picture you'll have CH, and in the other picture you'll have not CH. So the general idea here is, for a scenario for bifurcation, you want to write down everything you could hope for new axioms, and then prove theorems of the form, if you've got a sequence of axioms meeting those constraints, then you have a competing sequence of axioms also meeting those constraints, and one will have CH or one will have not CH, or one will have phi and one will have not phi for other sentences. In fact, it's not just CH, there's a radical bifurcation into a broad array of omega complete pictures. So the situation is this: if the omega conjecture holds, then existence fails, for third order arithmetic already. And if the omega conjecture fails, then existence may hold, so that looks like an optimistic scenario, but it's not very optimistic because uniqueness must fail, and so you've got bifurcation in that sense. And this scenario in which the omega conjecture fails and existence holds, and hence uniqueness fails, is an interesting one. And there's an analogy with special relativity, which I want to touch upon in the last few minutes. So prior to the advent of special relativity, it was thought that there was a preferred foliation of space-time into simultaneity slices, and one was living in what's now called Newtonian space-time. And it was thought that there was absolute significance to questions of the form, is A absolutely simultaneous with B? But then with the development of special relativity, we found a case where, for reasons internal to physics, that view became suspect. And now there's no absolute significance to statements of the form A is absolutely simultaneous with B. Rather, you have to pick a vector in Minkowski space, which is the replacement of Newtonian space, and that vector will give you a foliation of the universe. It'll give you a copy of Newtonian space, as it were, lying in Minkowski space. And if you pick a different vector, you get a different version of Newtonian space. So the analogy, which is a bit of a stretch, would be the following fanciful idea. Instead of the universe of sets, you have an analog of Minkowski space, and you pick a vector, namely a vector, a recursive sequence, and that gives you one omega complete picture of the universe. And then you pick a different vector, B vector, and that gives you a different omega complete picture. And CH is seen to not have absolute significance, but rather it's relative to a choice of a vector. Now that's a bizarre picture, and I have no clear idea of how to make philosophical sense of it. But I think that that's what one would have to do if one were to defend the idea of CH being absolutely undecidable or signaling a bifurcation. So in summary, I just want to say this is just one example of what I have in mind. And those criteria that I wrote down, omega completeness, don't exhaust all the criteria that one could ask for in new axioms. So it really is just an initial sample. But I think what we need to do is stand back and ask these two questions, which I want to repeat. What would it take to have an acceptable resolution of CH and other questions of set theory? And what would it take to have confidence that such questions are absolutely undecidable or signal a bifurcation? And we need to just explore the space of possibilities, and that's something I'm looking forward to talking to you about. Okay, thank you.
The fact that the axioms are complete in the sense of capturing the and the other that they be sound. That is, anything you prove in your logic is actually have you contemplated this question for omega logic? That is, I understand you're looking at the completeness aspect of omega logic, the axioms which in the context of that logic can be complete. But one must also examine the soundness of omega logic. And this sort of brings up, I think, a serious issue that perhaps a number of set theorists are uncomfortable with, which is whether verifying the implication of set generic extensions of the universe is sufficient to really establish the validity of that application. So that's my first question. The second is perhaps more specific with regard to reflection principles. Megador showed many years ago that supercompactness, which is generally accepted and consistent with the Cardinal assumption, is equivalent to, in fact, a conjunction of a hierarchy of reflection principles, a so-called gap reflection. And I'd be very interested in discussing with you to what extent these reflection principles might be posited as intrinsic based on your concepts.
Yeah.
As whether, in the spirit of taste reflection, these gap reflection principles can be viewed as intrinsic, and therefore as a way of providing the strength we're looking for in this super.
Okay. Concerning the first question, I think I need to get a bit more clarification because the soundness theorem is known to hold in the form that if T omega implies phi, then T omega proves phi. So you're asking for soundness in a different sense?
Yeah, and more basically, is it enough to look at such generic extensions in order to establish the validity of the statement?
Oh.
In that sense, I'm not comparing Lewis and technical syntactic with standard.
Right. So really what you're asking is, why not change...
What our concept of universe in set theory is, whether set genericity is really compatible.
Yeah. So that's really asking the question, why in considering omega logic do you only look at the space of initial segments of set generic extensions? Why not look at the space of initial segments of class generic extensions, for example? Yeah. The motivation for that is the seeming universality of set forcing with regard to independence for statements about L of R and things like that. With regard to independence of statements of L of R and things like that. So here's a question that I don't know the answer to, that if there's a proper class of wooden cardinals, can you find a natural statement about L of R that you can show is independent using class forcing? We know you can't with set forcing. Can you with class forcing? So I think the motivation for the restriction is just the fact that we don't have an answer to that question. Really, I don't. But that would be a great answer. I mean, a great question to answer. Regarding the second question, there's also the principles of Reinhardt, which are in his paper that has reflection principles in the title, and they give you one extendables and so on. But those principles don't say that properties about the universe of sets reflect to a level. Rather, they're more projection principles. Or you can have principles saying that there are two levels of the universe which resemble each other a great deal. And I've thought a lot about how one can try to give an intrinsic justification of those principles, but I haven't found anything, convincing. So, but yeah, it'd be great to talk about that.
Next question, sir. This may be outdated by these negative results, but I was under the impression that Uyghur agreed with Gödel that the continuum hypothesis is probably decidable or false.
Yeah.
Sounds a little different from this.
Yeah, I'm inclined in the direction that it's decidable, and I don't have any real view about whether it's false. I mean, it's the picture where it's false. There's a lot of statements, forcing axioms, which imply that the continuum is Aleph 2. There's an abundance of theorems which seem to be pointing at Aleph 2. I just think that we need to do a lot more investigation before we can settle on anything like that. So so really, on the first track, there are some scenarios involving, Wooden has some scenarios now involving an analogy between L of R and the structure theory of a very large model, L of E lambda plus 1. And there's conjectures about the parallel between those two, which could very well lead to new axioms that settle CH. So maybe I could just say something about that. In L of R, you start with V omega plus 1, and you build the constructible universe. And AD is a good theory of that model because you get that you can't change the statements by set forcing, and we know a lot about it. Then there's this other model, V lambda plus 1, and corresponding to that, you have an embedding axiom, which I'll write EI, though it has different names. And it turns out that, remarkably, the structure theory of this model, I should say this is at the edge of inconsistency. The structure theory of this model under this axiom is very similar to the structure theory of this model under this axiom, with the analogy omega is the analog of lambda 1. So for example, omega 1 here is measurable. Well, omega 1 is omega plus, so let's look at lambda plus. Turns out that that's measurable under this entirely different assumption. And the structure parallel is so rich that if you get a theorem here, you can start seeking for the analog theorem over there, and chances are you find it. But there's gaps in the picture. And one thing you can do is start adding the gaps. You can say, OK, based on the analogy A should hold, based on the analogy B should hold. And then there are certain questions which become open. For example, does this imply CH? Does this refute CH? So it could be the case that once you get the structure theory of this model, and that would be like a quasi-large cardinal axiom, you actually get principles that settle CH. So I want to explore both possibilities for an acceptable resolution and a non-acceptable resolution. But I want to sort of see where things end up before coming to some kind of conclusion about whether it has a determinate answer.
Well, I think we've already exhausted our time. And me. Let's take a speaker, please.